In this video, we'll talk about the last part of the pre-processing steps, namely smoothing, which is the final step basically that you do before starting statistical analyses at the single subject level. The question obviously that we should ask is, why should we deliberately blur the data? So now we've done a lot of steps to ensure that we have the highest resolution data, the smallest pixel, and we pay a big price for this because it's a trade-off between the size of the pixels and the spatial resolution and the temporal resolution that we make when we make decisions about the sequence that we use. And then the final step here, we decided to blur the data. Now, there's a number of reasons why we might do this. One is that it actually improves the spatial overlap. So in the previous step, we do spatial normalization across multiple brains, and there are some inaccuracies in transforming each brain and normalizing each brain to the template, to the normalization template. Although these steps are improving, and using the segmentation or the unified segmentation algorithm that SPM12 now offers gives some advantages and improves this step as well. So we blur over these minor anatomical differences and registration errors. And that means, well, the registration errors come from the algorithms, obviously, and the anatomical differences come from the fact that not everyone's, let's say, amygdala is in the same exact location. So the activations will be slightly different across different people, and blurring helps this these slight inaccuracies. Another reason is because when we average across different voxels, so spatial averaging, which is what smoothing is in principle, also suppresses noise. The idea here being that if the signal in two neighboring voxels is similar and the noise is randomly distributed, then the signal should be boosted by a signal or spatial averaging, while the noise should be relatively suppressed because we assume that the noise is random. So we're suppressing noise and increasing signal-to-noise ratio via this blurring. It has to be said, though, based on the matched filter theorem that is common in any kind of engineering application that has signal and noise, that the filter that we use needs to be chosen quite carefully, because the sensitivity is only increased to effects of a similar scale. So we have to make sure that we blur at a level, at a size, if you will, and we'll talk about the sizes in a minute, that also is of the same size as the expected activation. And here we will have some problems when we talk about cortical activations, which are typically rather large, versus subcortical activations, which are typically rather small. So we have to make some trade-offs there. Furthermore, blurring or smoothing, averaging makes the data more normally distributed, following the central limit theorem. And it reduces the effective number of multiple comparisons. That's the final point. So especially when we apply this to random Gaussian field theory, which we'll learn about in the future, you can think about this as leading to a lower number of actual comparisons that you need to do, and therefore you don't have to correct at the same level of family-wise comparisons. Finally, how is this implemented? Convolution is done with a 3D Gaussian kernel. So it's a simple Gaussian filter that I'm also showing up here. And it's specified at full width at half maximum in millimeters. I'll show you this in a second. What does spatial filtering do? So we're smoothing fMRI data in space. This is actually very commonly done. And this actually does this to the image. So this is a Gaussian filter applied to this image here. You can think about this as a brain image as well, but this was a more attractive picture than just showing brain images all the time. And you see that blurring with the Gaussian filter does exactly this to the image. here is the filter again. This is how the filter looks like. So you're applying this filter over the entire brain and sort of spatially averaging the entire brain. And we talk about this in terms of, so the filter size is determined by the width that it has at half of the maximum. So at the halfway point of this kernel, the width it has here, that's the filter width that we're defining when we smooth within SPM. And therefore, we talk about full width at half maximum, or FWHM. And typical sizes are between 2 times the voxel size. In our case, that would be 6 millimeters up to 10 millimeters. And here's an illustration about how this relates to voxel sizes, for instance. So we have about 4 times the voxel size at the maximum here, but it's about 2 times the voxel size at full width at half maximum. So what does smoothing do in a brain image? In principle, each voxel effectively becomes the result of applying sort of a weighted region of interest, and that's what we're showing here, right? So this is the original image. Once you apply a filter to this, you get this weighted average in a sense, such that neighboring voxels will increase so if they're activated, will increase the activation pattern that we observe in a specific region if there are many neighboring voxels that are activated. We can see this in an actual brain image here. So this is the unsmoothed data set. This is an image from the Poldrak book that you also have. When we use a small smoothing filter, so that's 4 millimeters at full width at half maximum. So it's a relatively small kernel. We get a little bit more activation, or larger activations, especially in the visual cortex. And you can see that each time you double this, it leads to smoother images. But you can also see that all of a sudden then activations disappear. So that's what we mean by if the activation size does not fit the filter, then you're actually losing signal, such as in the left hemisphere here. So this signal here, that's quite large here and quite significant, actually disappears here. So this is not a filter that supports or furthers this this type of signal. And that's a trade-off that we have to live with, especially when we talk about cortical versus subcortical activations, because they're relatively large in cortex, these activations, most activations, but they're relatively small because the regions are also small, such as in ventral striatum in subcortex. To summarize what we just went over, spatial smoothing increases SNR. That's why we do it, so that noise in one voxel will cancel out with that of other voxels. That's the idea behind any kind of signal averaging. When you average the signal, under the assumption that the signal stays about the same across different voxels that are highly correlated with each other, that do about the same thing in a given task, we assume that the noise is random across these two voxels. So averaging the signal should cancel out the influence of the noise. And the more you do this, the lower the influence of the noise becomes. A similar idea or principle is applied to signal averaging across different trials. And that's why commonly many trials are repeated, so about 40 within the same condition in functional magnetic resonance imaging, because this also leads to signal averaging. So this is one way that we can improve the signal to noise ratio. The assumption, however, that noise is spatially uncorrelated is not always true. We have respiration, we have cardiac pulsation, which obviously will be highly correlated across neighboring voxels. They will have about the same kind of effects of, they will see the same effects from these types of influences. Head motion is another one. Then the next question is how much smoothing should be done. That really depends on the spatial extent of the expected activation. And again, if you're interested in cortex versus subcortex, you should use different types of filters. A common recommendation is to use 2 to 3 times the voxel size. Then you have about, as a rule of thumb, a good chance to catch activations in both types of these regions. And that's about 6 to 10 millimeters full width half maximum. So the advantages, again, increases in signal to noise ratio. which will it will improve comparisons across subjects to account for sort of small anatomical differences across subjects. If you think about cortex, these differences actually become a little bit larger. So the signal that you're looking for may actually be somewhat spread across areas or regions of activation in cortex because of intersubject variability and because of some inaccuracies in the transformations that we apply when we normalize brains. The disadvantages are it reduces spatial resolution, and it's challenging to smooth accurately because the size and the shape of the signal is unknown. So here's an example of how activations actually differ in cortex. You can see they're relatively large in cortex, and in subcortex, such as the amygdala here, they're relatively small. And again, there we have different filters, and different filter sizes will optimize one type of signal, such as a large filter will optimize this signal, whereas a small filter will optimize this signal. And as we've seen in one of the examples, optimizing one type of signal will be suboptimal for the other type of signal. So you might not observe anything in the amygdala if you use a large filter. So again, use a filter that sort of provides a good trade-off of about 2 to 3 times the voxel size that you've used.